In this video, we are going to learn about cylindrical coordinates. So we'll define what cylindrical coordinates are and how to sketch curves given in cylindrical coordinates. And we'll discuss how we can recognize when and how to evaluate triple integrals using cylindrical coordinates. So in this video, we will talk about what cylindrical coordinates are. So they're a three-dimensional version of polar coordinates. So we've seen that a point P can be described in Cartesian coordinates, x, comma, y, comma, z. We can also do it in cylindrical coordinates, which will keep track of r, theta, and z. So z is going to be our regular Cartesian coordinate, so the z that we are used to. R and theta are going to be polar coordinates of the projection of our point on the xy plane. So visually, if I have this point, z is just this vertical distance to the xy plane like we're used to. And then if I look at this point down here, that's the projection. R is the distance from the origin to that projection. And then theta is like normal. It's the angle from the positive x-axis to this line. That's theta. Okay, so based on this, I can write equations to go from cylindrical to Cartesian or vice versa. So our usual polar equations are x equals r cosine theta. That's still going to be true. And y equals r sine theta. All right, and then there's nothing special with z, so z just equals z, because it's the same in cylindrical as it is in Cartesian. Okay, so with these, if I know the cylindrical coordinates, if I know r and theta, I can plug them into these to get x and y. And if I know z, well, it's the same z in either. If I want to go the other direction, I can do Pythagorean theorem in this right triangle. That'll give me r squared equals x squared plus y squared. If you use tangent in this triangle, tangent of theta equals y over x. And there's nothing special for z, so z just equals z. So with these, if you know the Cartesian, if you know x and y, you can plug them into this right side and then use that to figure out r and use it to get theta. Okay, so let's do an example. So I want to sketch the following graphs, which are given in cylindrical coordinates. So in part A, I have r equals 2. So notice there's no theta or z in this, which means theta and z can equal anything. They can take on any value. So let's go ahead and draw our axes. So I'll draw the z-axis, the x-axis coming out at a slant, and the y-axis over here to the right. And then I'll draw the negative versions of these, the negative y, the negative x into the page. Negative z would be down. Okay. Just to get myself ready, I'll copy these axes and paste it over to the right where I'm going to do part B in just a minute. Okay, just to get ready, I'll draw it here too. Okay, so I know that in polar, r equals 2 would just be a circle of radius 2, center to the origin. So let me start with that. Let's start with that. If I draw radius 2 circle, center of the origin, so that would be something like this. Something like this, where this is 2 and this is negative 2 and that's negative 2. Okay. So the fact that theta can be anything means I take all these points where r is 2, distance of 2 from the origin. The fact that z can be anything means that at any of these points, I can go as high up as I want and as low down as I want, no matter what point I'm looking at. So that's going to extend this circle up and down, and it's going to turn it into a cylinder. At all of these points, I'm going to extend it up and extend it down. It'll turn it into a cylinder. So if I draw some more cross sections, it's got these circular cross sections. So we get this cylinder. We get a cylinder where the radius is 2. Okay. So cylinders have really simple equations in cylindrical coordinates, which I think is kind of what I'd expect. All right, part B. What if r equals 2 and theta equals pi over 4? So there's no z, which means z can be anything. Z can be anything. So, okay, if I start with theta, theta is pi over 4. So from the positive x-axis, I'm going to make an angle of pi over 4. So make an angle of pi over 4. That equals pi over 4. And then I'll draw a line coming out this way. And along that line, I have to go a distance, r equals 2. So if I go that distance, maybe that'll put me somewhere here. And that's a distance of 2. The fact that z can be anything means from that point, I could go as low as I want, far down, and as high as I want, up. So that creates a line. So this is the graph of a line now. Okay, nice. So let's do a couple more examples. Okay, so next one, z equals 1 minus r squared. So I'll talk about two different ways to do this. The first is, let's try converting this to Cartesian coordinates. And maybe I get lucky and it's a shape that I know how to graph. So z equals 1 minus, and I know r squared is x squared plus y squared. So if I distribute the negative, z equals 1 minus x squared minus y squared. And this might be a graph that we recognize from earlier in multivariable calculus. This is what's called a paraboloid. And these negative coefficients in front of x squared and y squared mean it's going to be a downward paraboloid. So if I draw my axes, so if I draw the z-axis, x-axis, and y-axis, draw the axes, I'll also draw the negative directions. So negative y, ooh, let's draw that better. Negative y, ooh, negative y coming straight to the left. Negative x going into the page. Negative z going down. Okay, and then just to get myself ready, I'll copy this and paste it to the right when I draw the graph for part D. Okay, so, all right, so this value of 1, that's going to be the z-intercept. The z-intercept at 1. So now I'm going to go ahead and draw this downward paraboloid, 3D parabola. So when I do that, I'll draw a couple of different sort of arcs of this paraboloid. So I'm going to draw kind of down like this, down like this. This is, I'm trying to draw it on the YZ plane, where it's going to hit 1 as this y-intercept and negative 1 over here. Kind of like y equals 1 minus x squared. It's got these intercepts at 1 and negative 1. If I draw the same type of thing, but on the zx plane, I'll try to put this in a different color. It would kind of come down like this. Ooh, oh, except I want to make it curved. It would come down from that top point. It'll hit 1 here on the x-axis and keep going. If I go in the negative direction, I'll try to draw it dotted. It'll hit negative 1 and then keep on descending down. Okay, so as part of this, notice that if I draw the intersection on the xy plane, it's hitting either 1 or negative 1 on the axes. Okay, and that's the intersection on the xy plane. Okay, so I get this 3D paraboloid. That's one way I could graph it. Another way is I can first sketch the graph in the ZR plane, because there's no thetas in this. So if I just draw the graph in the ZR plane, so I'd make an axis for R, make an axis for Z, then this graph would kind of be like the graph of y equals 1 minus x squared. It'd be a downward parabola, where this z-intercept is at 1, and the r-intercepts are at 1 and at negative 1. And visually what this means is these values of r represent how far out am I from the origin, just on the xy plane. So this would be like a distance of 1 on the xy plane. But there's no value of theta that's given, so I could be anywhere a distance of 1 away. Anywhere a distance of 1 away. Okay. And what I'm going to do now is, because of that, we can rotate this 360 degrees, take all the theta values around the z-axis. So if I rotate this whole graph around the z-axis, we'll twirl this parabola around it, and when I do that, it makes this 3D paraboloid. So that's another way to see that the graph is going to become this. Okay, nice. So let's do one final example here. What if I have z equals r and r is greater than or equal to 0? So first, let's convert it to Cartesian. So I have z equals, and r squared is x squared plus y squared. So r would be the square root of that, x squared plus y squared. And we might recognize this equation from multivariable calculus. This is a cone. This is a cone. Okay, if you didn't quite recognize it's a cone, you'd have to remember, how do we graph something like this? And that's, we can use what are called level curves. Use level curves. Okay, and the idea there is you pick values for z, like for example, you could do z equals 1, and then sketch what that would be. So that would give you 1 equals square root of x squared plus y squared. If you square both sides, you get 1 equals x squared plus y squared. So that's a circle of radius 1, centered at the origin. At the height when z equals 1, so that means when z equals 1, you'll get this cross section, this circle. I go a distance of 1 in each of these directions. Something like this. That's one of the cross sections. At a height of z equals 1, that's what the cross section looks like. And you can keep doing this. You could pick like z equals 2 and so on. It turns out that if you do that, you get bigger and bigger cross-sectional circles. And if you connect them, what you get is a cone. You get this cone. It's not a perfect picture, but you get this cone. If I draw some more of these cross-sections, the cross-sections are circular. Okay, so nice. Another way I could graph this, because there's no theta in this equation, is I could go to my RZ axis. So I can draw my R axis and my Z axis. One other comment that I want to make is, what does R greater than or equal to 0 mean? If I didn't have this, the cone would also extend downwards, because R could be negative. But because R can't be negative, Z cannot be negative. It's just the top half. Okay, so the graph of this on the ZR plane is just a line. It's actually just part of a line. It's just this half of the line. Because R is greater than or equal to 0, we don't have this bottom half. And now if I take this and I now rotate this, now we rotate around the z-axis, because there's no thetas here. Theta could be anything. We rotate it around the z-axis. Well, if I twirl this line around the z-axis, it's going to form a cone shape. And I got my graph. So we have learned what cylindrical coordinates are and how we can sketch curves given in cylindrical coordinates. Over the next few videos, we'll look at how we can use triple integrals using cylindrical coordinates and how to tell when we should use them.